Hello, this is Dr. Strickland. In this video, we will investigate the principles of volumetric analysis. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So, we're going to talk about the principles of volumetric analysis. Volumetric analysis is just the part of analytical chemistry that deals with titrations. And titrations are a large and powerful group of quantitative procedures based on measuring the amount of a standard solution that is consumed by an analyte. Remember that an analyte is the chemical component of a mixture that you're interested in. So a titration can be based on a bunch of different kinds of reactions: acid-base, redox reactions, precipitation reactions, or the formation of a complex ion. So we're going to talk in the context of the standardization of an approximately 0.1 molar sodium hydroxide solution using primary standard potassium hydrogen phthalate, because you've done this one. Okay, so the purpose of the experiment was to determine the exact concentration of sodium hydroxide in this solution so that the solution will be standardized. And when it's standardized, then its molarity will have 4 significant figures, which can then be used to determine a fair level of detail in whatever you might want to use it for. Now, if you try to make a sodium hydroxide solution out of solid sodium hydroxide is a funny chemical because it will not only absorb water out of the air, that makes it hygroscopic, but it will also react with carbon dioxide in the air and make some sodium carbonate or some sodium bicarbonate. So in order to combat some of that, we use the 50% sodium hydroxide solution, but it's not foolproof. So we do an approximate concentration and then we standardize. So the balanced chemical equations for this process involves the KHP, and I'm going to draw the KHP like this. So there's a carboxylic acid there and a carboxylate group here ortho to it that has a potassium counterion, and this is KHP. And it reacts with sodium hydroxide. And sodium hydroxide is just a classic base. And what it does is it deprotonates the carboxylic acid to form water and a second carboxylate. So you've not only got a charged functional group right here, but now you've got a charged one up here also. So just an acid-base reaction. So we'll put that right here. All right. So in order to standardize this solution and find out exactly what its concentration is, we need a primary standard solid, because a primary standard solid can be weighed out and directly used to provide a known number of moles because the solid is particularly stable. Starts out with a very high purity, won't decompose under normal storage. It's not hygroscopic like sodium hydroxide is. It's stable when dried by heating to remove surface moisture. So with hygroscopic solids, even if you dry them in the oven, you can't get all the water out because it's not all on the surface. All right, so a standardized solution having 4 more significant figures can then be used in a second titration to determine the exact concentration of an analyte in a sample. Like, for example, if you had an unknown, got a granular solid that had an unknown percentage of KHP in it, which you will have done all as well. Okay, so that's what you need it for. You need it to determine the exact concentration of an analyte in a further titration. This is also going to involve having an indicator. And in these 2 titrations, the standardization of the sodium hydroxide solution and then the use of the standardized solution to determine the unknown percentage of KHP, we use phenolphthalein. And phenolphthalein is probably the best known acid-base indicator. But any indicator is a compound with a property, usually color, that changes abruptly when the equivalence point of a titration is reached. So with acid-base reactions, generally speaking, um, it's one color in acidic solution and one color in a basic solution. So the indicator will help you with the equivalence point and the end point. So the equivalence point of a titration is reached when the number of moles of titrant added is exactly enough to react with all the moles of analyte in the sample. And this is a chemical change. You add the stoichiometric amount of, of the solution in the burette to whatever you've got down in your volumetric, in your Erlenmeyer flask. Okay, so, but most chemical changes are invisible. You need something else in there to tell you when you got there. So the end point of a titration has to do with your indicator. So the end point of a titration is the first hint of this change in the indicator's physical property. So with phenolphthalein, you start out with something acidic and you add base to it. You're watching this colorless solution and you want to know when it just faintly turns pink, the very half drop that changes it from colorless to pink. So this is a physical change. And these two processes are going on simultaneously. And we'll talk more about that down the road. Okay, but this little bit of a difference between the amount of titrant needed to reach the end point and the amount needed, this says the same thing. Let's say the amount needed to reach the equivalence point. Let's go ahead and just change that right here. And the amount needed to reach the end point. Okay, so it takes just a teeny bit more to reach the end point. So the better you can detect changes in color and use half drops, the smaller this difference will be between the amount that was needed to donate exactly the right number of moles and the little bit extra that you needed to make the color change. So this difference can be quantified by titrating a blank sample and subtracting the blank volume from the titrant volume used. All right, so that's the basic story on the principles of volumetric analysis, some of which you've used and some of which you will use. If you have any questions, please send them to me.